Good morning. Happy week 10. Thank you for braving the weather to be here with us today. So today is the first of three lectures on special topics in polymeric materials. So today we'll be talking about polymers in nanofabrication. So that's micro and nanofabrication. It's de facto nanofabrication, but we still call it microfabrication. And then we'll talk about so all of what I'm going to talk about here, most of it is actually commercialized already, and probably you have examples of this stuff in your pocket already, and in your laptop and TVs and so on. On Wednesday, we'll talk a little bit more about a topic that's more sort of at the not yet commercialized stage, which is polymer solar cells. So we'll talk about solar cells in general and what polymers can do to contribute to the energy challenge. And then on Friday, we will have a guest lecturer, our illustrious TA Sam Root, who will give a talk on computational material science in as it relates to polymers. Okay, so why do we care about nanofabrication? So why do we care about nano to begin with? What we want to do is to make, understand, and control materials and phenomena that occur on the scale of 1 to 100 nanometers. So this is kind of the textbook definition of nanoscience, nanotechnology, that at least one dimension of the material has to be nano. Probably 2 dimensions, because the Scotchgard coating on your glasses, if you wear them, or your windshield is probably 100 nanometers or less. And is that nanotechnology? Maybe. Is it really that important? Whether it is or not, I don't think so. So materials and phenomena that occur on this scale are, for example, the size and size-dependent photoluminescent properties of semiconductor quantum dots, the strength and exceptional charge transport characteristics of graphene and carbon nanotubes and buckyballs, the adhesion of gecko feet to planar surfaces. So atomically smooth surfaces, a gecko will still stick to it. It will still stick to a polished surface of a silicon wafer by van der Waals forces. This is the Lycurgus cup, which is a Renaissance glass piece of artwork that has this red color that's actually derived from plasmonic gold nanoparticles embedded in the glass that actually resonate and scatter light at a certain frequency that depends on the size of the gold nanoparticle. And I put this last example here, so microprocessors and memory devices, as an example of nano, because this is probably the most commercially successful device made using nanofabrication, because I mean they're ubiquitous. They've really enabled everything that we take for granted in information technology and the internet and everything. But the ironic thing is that these are very much classical devices, and the effects of size confinement that we associate with nano, like quantum tunneling, are really regarded as something to be suppressed as opposed to something to be exploited, because you don't want electrons tunneling from one transistor to the next, or tunneling through the gate dielectric, for example. But this is actually what we're going to talk about today, even though we don't really consider this nanotechnology. I do, but the field generally doesn't. In any case, the future of nano is regarded as the future in some sense of medicine, catalysis, separations, sensing, information technology, and energy in both the conversion and storage aspect of the energy challenge. So let's talk about nanofabrication and nanomanufacturing. Nanofabrication is the generation and arrangement of structures with sizes that are usually the lateral sizes of 1 to 100 nanometers. So arrangement is important because you can always generate a nanostructure by some colloidal synthesis, but then you need to get the particles in the right spot in a 2- or 3-dimensional architecture in order for it to be considered nanofabrication. The first step in nanofabrication is mastering, which is the creation of new nanoscale information where no nanoscale information existed before. So the key to the mastering step is you need to be able to create this nanoscale information in a form from which it can then be replicated. So a good example of this is scanning beam lithography, which can make one copy of the mask in a photolithography system per day. So you can shine an electron beam, you focus an electron beam into a polymeric resist material that we'll talk about in a few slides, and that beam will very slowly carve out the patterns in each layer of the microprocessor. So you'll carve out the patterns in a mask, then you'll use that mask to project on another film that's sensitive to light. I'll show you what that means. So this is an example of an electron beam writer. It is actually a converted scanning electron microscope. Do you know what a scanning electron microscope is? Basically, you shine electrons at something, and because electrons can have a smaller wavelength than photons, trust me, it gets really good. Time will tell, I guess. So a scanning electron microscope rasters an electron beam around and then detects the secondary electrons that are scattered off the sample, and that's translated into an image. An electron beam writer is the same thing, except it's using the beam not to image, but actually to etch patterns in an electron beam sensitive polymer material. So we're going to write this pattern, and where we write the word pattern, this region becomes soluble. So then we can dissolve this pattern out, and then we can get rid of the green stuff, which is our polymeric e-beam resist film. Then we can etch some layer to create this pattern in the master. So this system here it's about a few years old. This is an old price, but $2 million, chump change. Here is e-beam resist chemistry. So we take this is polymethyl methacrylate, which is a very famous electron beam resist material. You can generate patterns of about 10 nanometer line width in it. And it undergoes these homolytic cleavages here to generate, to break the material apart, so that you can then flow solvent over this material and dissolve out the little molecules that into which the polymer has fragmented based on irradiation with this electron beam. This is polymethyl methacrylate. It's a positive resist. So positive resist means you get the image that you create. Duh. What else could it possibly mean? You get the inverse. In the case of a negative resist, you get the inverse image of what you're patterning. So in the positive resist, you shine your electron beam, and where you shine the electron beam, you get holes in the resist film, basically. In a negative resist, based on, for example, epoxides, this is called SU8 photoresist, and you have a photoacid generator, and it opens this epoxide ring. Don't worry about the chemistry, but the point is that this material cross-links in the presence of irradiation. So you cross-link it in the presence of irradiation. So instead of getting holes in the film, the film becomes hardened where you expose it to the electron beam. So positive resist, negative resist. So once we have these master structures, the second step after mastering comes replication. Replication is copying the nanoscale information from the master. So photolithography, for example, can make a 300 millimeter wafer about 1 per minute. So 300 millimeter wafer goes into the photolithographic stepper, and light shines through the mask that we made using e-beam lithography, and that pattern is transferred to the photoresist film on the final wafer, and that can go very, very fast. So E-beam was 1 copy per day. This is 1 copy per minute. So here's what I mean. This is the mask we made by E-beam lithography. Then we shine light through it, and we get these patterns. And because this is a blanket exposure, we can do it very fast. This is a 193 nanometer exposure tool called a stepper, and it comes at a price of about $30 million, probably closer to $50 or $60 million now, because now these 193 nanometer light sources are used to make much, much smaller features. So most of the cost is actually embodied in the precision with which these mirror elements, mirrors and lenses, need to be positioned in the device in order to scale down the image and get it to impinge exactly where you want it on a wafer. Because a microprocessor, so the Intel Core M or whatever, has up to 50 layers of photolithography that all have to be very precisely registered. So here's a schematic diagram of what I mean by positive versus negative resist chemistry. So here is a substrate. Say this could be a silicon wafer. You have a resist film on the top. Then the mask here, which is where we have these holes that have been etched out by E-beam lithography. And when you shine light through a positive tone resist, you expose these areas, they become soluble, then you can get rid of them, then you can etch or dope or do ion implantation into the substrate in whatever way you want. Then you strip off the rest of the polymeric resist. In a negative resist, you harden this material that's exposed, and then you can etch the material around it or modify it or do whatever you want to it. So here's another example of a photoresist chemistry. This is called Novolac or Bakelite sometimes. And what is done is this polymer is mixed with this guy called diazonaptoquinone that under UV irradiation decomposes by expelling nitrogen gas into this carboxylic acid product, which is then sensitive to dissolution in aqueous base. So typically tetramethyl ammonium hydroxide is what is used to dissolve this and then expose this to dissolution. So this is called a DNQ Novolac style resist. This hasn't been used industrially to make the highest end microprocessors in many years, but it's still used for lower resolution, for applications needing lower resolution, and it's used ubiquitously in academic labs. So does anybody happen to have been in the clean room at UCSD? Couple people? All right, great. So you probably perhaps have even used DNQ Novolac type resists. The solvent smell is a very distinctive odor. Anyway, so these processes are probably the most sophisticated manufacturing processes ever employed for a commercial product. Wow, those are some fighting words, right? They seriously are. Sometimes I'm amazed at just how precise these things can be and what low rates of error you can get from them. So does anyone know what the acceptable, you're making memory devices and there's some yield that you'll get. Does anyone know what the maximum acceptable rate of error is in a high-end microfabrication? It's 1 in 10 errors. 1 in 100 errors, 1 in a million, 1 in a billion, 1 in a trillion, 1 in a quadrillion. It's 1 in 10 to the 18. So that's approximately the number of errors that can be produced. And if you get more than about 1 in 10 to the 18, then they have to redesign the process. Because it doesn't make sense to build a $3 billion fab that's full of $50 million stepper equipment and to get that kind of a rate of error. So I don't know, microprocessors, commercial aircraft, biologic-based therapeutics. There's some aspects of technology that are just so precisely engineered that it just boggles the mind, like that this stuff actually works as well as it does. So this is Moore's law. Moore's law predicts a number of things, but one manifestation of Moore's law is that the transistor count on a microprocessor doubles approximately every 2 years. You can plot this on a log scale versus time, and this, at the time, we were getting about 1.5 billion transistors per microprocessor. And you can see, you can look on this plot and figure out where your first computer was. My first computer was here, and we had a 486. So we went from about 500,000 transistors to 1.5 billion. I don't know, I just got that laptop. It's probably like 3 or 4 billion transistors now. The 486, only 1 million transistors. Crazy. You got that on October 10th, 1993. I remember the date for some reason. It's also the date that I watched my first original Star Trek episode and got hooked forever. Because my sisters wanted to use the computer, the new computer. I'm like, okay, I'll watch whatever's on at 11 p.m. On Fox, and there it was. Okay, fascinating. What are the limits to photolithography? So if we're using photons, so this is not the limits of e-beam lithography. E-beam lithography, we can go almost as small as we want, a few nanometers. But we can't manufacture with e-beam lithography yet. We can't manufacture with e-beam lithography, although some people are trying to do it using millions of electron beams all at the same time. But we can manufacture with photolithography. But if we're using photons, there are many complications that arise in using photons, one of which is quantum mechanical. So photons diffract. When they go through an aperture, they diffract like a wave, and the image gets blurred. That is the fundamental problem. So the resolution is limited by diffraction. So resolution equals k lambda over the numerical aperture of the lens. So our minimum feature size possible, sometimes this is called the half pitch. The half pitch is the, roughly speaking, the spacing between adjacent devices on a memory chip or a microprocessor. The full pitch is the kind of the wavelength. If you just make lines, the pitch is the wavelength, and the half pitch is the spacing. So K is the proportionality constant, which is a system-dependent parameter that reflects sensitivity of the system to exposure, in exposure intensity, temperature. So temperature, thermal expansion, and contraction, when you're talking about making devices that have line widths of only 14 nanometers, if you have a little bit of thermal expansion and contraction, your resolution goes to crap. So you must be stable to within thousandths of degrees Celsius or Kelvin. Currently, proportionality constant 0.3 is considered good, and the industry says it's impossible to get this below 0.25. Lambda is the wavelength that is currently uses 193 nanometer light from an ARF excimer laser. Anybody know what company produces this laser? Anyone heard of a company called Cymer? Know where that originated? At UCSD. Was actually the founder's PhD thesis at UCSD. And since then, Cymer was acquired for the billions of dollars from the Dutch company ASML, but that was about 2 years ago. So now, so we still use 193 nanometer laser light to make 14 nanometer features. How do we do that? The 157 nanometer light has been abandoned because while we could, in principle, shrink the feature size by using shorter wavelengths or higher energy photons, the lenses and immersion fluids, what's that? I'll get to that in a minute, absorb this light. 193 nanometers seems to be about as short a wavelength as you can get before the components of the system start absorbing the light, which you don't want. So extreme UV, like 20-some nanometer, and X-ray light is considered the next generation, but there's no clear pathway to getting there. So the numerical aperture equals n sine theta, which is the acceptance cone of an optical system, and it's proportional to the refractive index of the medium. It's a polymer class, that's all I'm going to say. How do we beat the diffraction limit? So if you bought a computer anytime in the last year, and it has the most recent microprocessor in it, it will have a feature size of 14 nanometers. It's pretty incredible. 14 nanometers, just the diameters of, on the order of 10 atoms wide, which is crazy. 14 nanometers, but we're using 193 nanometer light. How do we do that? So current processors have 14 nanometers, so the Intel Core M is an example. One of the approaches that we use, not me, but people that work in this area, many of you will actually be working in the microelectronics industry because it's probably the, one of the top employers of nano engineering and chemical engineering students, is you use emergent optics. So you project your light through a medium with a higher refractive index than air. So what's used? Air has a refractive index of 1, and water, pretty cheap, benign liquid, easy to get it to high purity, has a refractive index of 1.33, which is actually quite high for liquids. Also used are phase-shifting masks that produce interference patterns at the edges of features in a mask, and this shift in phase can actually produce sharper boundaries between features or new features in a photoresist film that have a smaller dimension than the diffraction limit would allow. Here's an example. So suppose here's the unphase shifted aperture, and here is a here's the same aperture but with a phase shifted region where all of the ups are in parallel with the downs over here. So what does that do? And how do you create a phase-shifted region? Well, you shine light through a regular mask, and you have opaque elements, and everything goes through. Okay, that's fine. But what if you take a little bite out of one of the regions? Or what if you permit only partial transmittance through one of these formerly opaque elements? That will actually produce a shift in the phase. So what happens in a conventional mask is if you have two apertures that are too close together, the field amplitudes will overlap because of diffraction. And when they overlap, you'll get a superposition of field amplitude, which will correspond to an intensity which gives you one feature. Even though you had two apertures, you get only one feature. However, if you have a phase-shifted region that's produced by either a partially transmissive element or an element that is slightly thinner or slightly thicker than the adjacent element, then you get field amplitudes that are out of phase and a superposition that are in phase here, out of phase here, and the intensity, so the square of the superposition, is now two features instead of one feature. So that's a way to beat the diffraction, because normally you had spillover through these lines to give you one peak. Now you have two peaks. So another approach is to use multiple exposure patterning, and this is where polymer chemistry can really help out the system. So what is normally done to beat the diffraction limit is to take two different resist films. So you coat one resist film. You do this by a technique called spin coating, where you take your giant wafer and you extrude a polymer solution on the wafer, and then you spin it at several thousand RPM, and you expel all of the stuff off of the wafer from the edges, and the film becomes very thin and very uniform. That's how you get the photoresist film on the wafer to begin with. Okay, so you spin coat the resist, and suppose the goal is to get something with this half pitch, so a very tight half pitch here. You can't pattern this directly because you'll just get one big feature because of diffraction. Your lines will just, your light will just spill out and diffract everywhere, and you'll get nothing here. So the idea is, can we take one resist film and pattern it at half the half pitch, or at twice the half pitch? So this, then spin coat another resist film, and then expose that to get twice the half, to get the half pitch that we want. So we use two different masks and two different photoresist films, but we're only patterning one layer. So we've doubled the half pitch, or we've halved the half pitch, but we've increased the resolution. How about that? No more halves and everything. We've increased the resolution, but we've doubled the number of masks that we need, and we've doubled the number of photoresist coating procedures that we needed. So if you have 50 layers in a device, you now need 100 steps to make the 50 layers. So that's not so good, right? We want to find a way to make that better. So why can't we just keep this same resist film, but then take a second mask and expose the same resist film right here and right here using this mask? Why wouldn't we be able to do that? Use the same photoresist film, but use two different masks. Why couldn't we do that? The reason we can't do it is because the edges of this film have been exposed by diffraction. And in order to use a different mask to get the features here and here with the same resist film, the resist film in the diffracted regions would have to forget that they've been exposed already. So these are sub-threshold exposures that need to be forgotten by the polymer film. And so far, there aren't really any good ways of doing that. What you would like to do is called double exposure. And this is an active area of research in the microelectronics community because it could potentially half the number of steps that you use to get a high-resolution pattern, is to make a photoresist film that has the property that it can forget sub-threshold exposures. So you expose once, then you get a new mask, and you expose the same photoresist film again. Again, the reason you couldn't use a mask that had the features, that had all the features you wanted to begin with, would be, again, because of diffraction. You would just get exposure everywhere. But between here and here, this photoresist film has the property that it could forget the sub-threshold exposure in the diffracted regions around the exposed regions. Does that make sense? Another cheat is to use methods of edge lithography, where you take again, suppose you want, again, this very high resolution pattern, but you're starting with a much lower resolution pattern. What you can do is create features in this resist film, and then deposit some spacer, which could be some oxide or some polymer deposited by chemical vapor deposition or something, and those sidewalls become the new resist features. So the sidewalls of those features double the resolution because you have two sidewalls per feature. And then you use those features to direct the etching to get the resolution that you want from a mask that had half the resolution. So multiple exposures are very expensive because it doubles the number of steps Actually, more, yeah, it doubles the number of steps. It's also hard to register things with tens of nanometer resolution. So double exposure is promising, but it requires new resist chemistry. So this is a very active area of research, while these two are already done. This is really, this process is quite ubiquitous, actually. This is interesting. So this is a survey taken in 2008, so 8 years ago, at the CEMATEC conference, which is the Semiconductor Trade Group. And they had all of the experts in photolithography from Canon and Cymer and ASML and Intel and Texas Instruments. And they said, what are going to be the most prominent approaches to photolithography by 2016? So it happens that this year is 2016. So let's see how accurate the experts were. 193 nanometer single exposure, which is without the double exposure, was expected to go down, and indeed it has. It's really not done anymore to make the highest end products. This is 193 nanometer immersion double patterning lithography. They expected to get another 4 years out of this before it went down to almost nothing. And they expected extreme UV lithography to go way up and maskless lithography to go up exponentially to steal for a little bit of the extreme UV's thunder. What has happened is that extreme UV is down here, and maskless lithography, which was on this exponential curve, which was going to be up here, is also down here. 193 nanometer immersion double exposure patterning is like here. So we've managed to, wring more and more resolution out of the same process, but it's probably going to end soon. They always say that. This time for sure. If you look up, so I'm not one of those professors that will say don't trust what you read on Wikipedia. Much of it is actually useful. They have this really nice plot, this really nice chart on the Wikipedia article for next generation lithography, which will go through all of these approaches that we've talked about. So this is still the current approach. Okay, so in the research lab, we usually don't do high-end, well, we never do high-end photolithography because you need, $3 or $4 billion fab that is only really built by companies like Intel, AMD, Samsung, Texas Instruments, and so on. So how do we do nanofabrication in the lab, and how do we use those same processes for potentially industrial processes that require fabrication on non-planar surfaces or stretchable or wearable devices? How do we manufacture nanostructures using polymers in ways that don't require the same kind of high-resolution photolithography that the microelectronics industry uses? One reason we don't want to use the high-end stuff is because of the high cost. So tens of millions of dollars to get a stepper. Sometimes accessibility can be a problem. So at UCSD, we're lucky to have the Nano 3 clean room, which is like an 8,000 square foot class 1,000 clean room, which means 1,000 particles of half a micron or less per cubic foot of air, which is, believe me, considered low and good. But clean rooms use a lot of energy. So this was a book chapter that I wrote a couple of years ago on the energy usage in a clean room. So if you take the clean room that we had where I went to grad school, it took 27 million kilowatt hours per year to run the clean room, which was 2% of the energy bill of the entire university. Most of that was the tools, so the electrical energy bills. So clean room equipment tends to be under high vacuum or high temperature, something that requires pumps and heating elements and thermoionic emission of electrons, all very high current, high voltage equipment. And then the balance of it was on environmental controls. So in industry, a fab will actually have a reverse energy footprint where the air handling and air conditioning and air filtration will actually take up about 2/3 of this pie. But in academics, it's about like this. So often we want to pattern unconventional materials like DNA microarrays for like alumina, for example. Want to pattern organics, biologics, and they're incompatible with the tools, and often they're not even allowed in clean rooms. We're often interested in unconventional form factors, to use a Bill Gates word. So a form factor is something that, you could have a rigid form factor like a wafer, or you could have some stretchable or wearable form factor for like a Fitbit or something. Also, very small devices and disposable devices are of interest. There's an issue of overkill, that chemistry, biology, sensing, medicine, optics, and materials for energy tend to be more tolerant of defects than microprocessors. What if 1 in 100 error rate is okay? You don't need 1 in 10 to the 18 error rate. And then, because this is often, because we want to have fun in inventing new nano manufacturing strategies, there's the issue of, there's an idea that nano has to be something that's difficult. So nano clean rooms, bunny suits, e-beam lithography, and so on. But nanoscale information is really all around us in nature. It's just a question of how do you find that nanoscale information in a form from which it can be replicated. So nano information exists in cracks, shadows, edges, sidewalls, defects, lattice steps, and other discontinuities. One of the approaches is to repurpose an analytical tool for the purposes of fabrication. So if you look at the history of nanofabrication, most of the tools were actually developed for imaging, not for production. So the optics used in photolithography were derived from microscopes. The e-beam writers were actually derived from electron microscopes. So often we take something that was made for analysis and we repurpose it for manufacturing. So this brings me to this topic of soft lithography. So soft lithography is different from e-beam and photolithography in that it uses a polymeric stamp to mediate the transfer of a pattern. So usually the master for photolithography or master for soft lithography is some silicon wafer that has trenches etched in it. So we can master it by the same approaches that we use in regular lithography. But the key step here is then once we have this master, we pour a silicone rubber prepolymer on it, and then we cure it and peel it off so that the silicone rubber polymer now has a stamp. Now is a stamp that has nanoscale features in it. And that stamp can be used on flexible, stretchable, non-planar surfaces and can be used, and it can also pattern things like inks, like biomolecules or conductive polymers or self-assembled monolayers or quantum dots, things that can't be patterned directly by photolithography. So you can use this silicone master in a number, or the silicone rubber stamp. This is the pattern transfer element, so to speak, by decal transfer printing. So you ink the stamp with something and you stamp it. Or you use it to mold and emboss in a thermally or UV curable prepolymer. You can also use phase-shifting edge lithography, which is sort of like phase-shifting masks that we talked about before, except you're actually putting this in contact with your resist film, and then you can get features that only appear around the edges of your your topographic features. Then you can also use other approaches to edge lithography. This one is called nanoskiving, which is what I did my PhD thesis on. And you take this thin film of a metal on these epoxy polymeric replicas. Then you can section this with a deli slicer to get a final pattern that has only the sidewalls of the original master. So you can get 10 nanometer features using this from a stamp that has micron scale features. So this is molding using a soft stamp. So you take a silicon wafer, you do photoresist chemistry on it, you pour a PDMS, polydimethylsiloxane, or silicone rubber prepolymer on it, you cure it, peel it off, and then you use it to mold a final substrate. You can also do this over non-planar surfaces. So this is this is an elastomeric backing with a thin film that has a relief pattern in it of a higher modulus polymer that we make it higher modulus so that these features don't collapse into each other. And this can be used to pattern the sidewalls of optical fibers, for example. So this is a different approach to replica molding, where you can take a block copolymer film that is a PMMA block polystyrene film. You expose the PMMA phase to UV light. You rinse it with acetic acid to make just these polystyrene films. Then you can generate these PDMS stamps that have these bubble features in them by, who knows why you don't want to do that, but basically what you can do is take this block copolymer structure and then translate it into a mask, and then turn that pattern into use it to pattern materials that can't be patterned directly. So how thin can you actually replicate a pattern in a silicone rubber polymer? Turns out to be less than a nanometer. So to do this, what the researchers decided to test what the limits were, what they did is they took a silicon wafer that was single crystalline. Then they glued a glass slide to one side, or to one half of the bottom of it. Then they put a crack in the silicon wafer, and then opened up the crack so that the crack stopped where the glued piece of glass was. So the crack went from a few microns all the way down to flat. So the crack was like this, and at some point the crack stopped, and where the crack stopped, it went from cracked to not cracked. So that is in principle the smallest step edge that someone could potentially measure, and it can be measured and it can be replicated. So 0.4 nanometers, which happens to be the van der Waals diameter of a silicon atom. You can also make very high aspect ratio structures. So these little octopus arms here are 8 microns tall and 250, like 500 nanometers at the base, about 250 nanometers at the top. This is actually some unintentional artwork by me, where in an E-beam evaporator, sometimes you'll get these gold spheres. So electron beam evaporator of a metal, you'll get these gold spheres that are sometimes ejected. And this one happened to have been caught in midair by these two polymer octopus arms. And, we'll never see that again. Wish that was useful. You can also use these approaches to make interlocking structures. So how do you make a 3D structure like a solenoid or this letter A that has holes in it? So what you can do is you can create a master by a process called two-photon lithography, which is a way of using two laser beams that undergo constructive interference at a certain position where they intersect. So like in Ghostbusters, crossing streams. So you actually want to cross the streams here. And you get a constructive interference. in 3 dimensions, and you can carve out these structures. Now the key is if you make this structure with this membrane in between, because you can't make it without a you can't automatically create you can't replicate something that has an interlocked structure, because you'll never free the final structure from the master if it's got this hole in it. So what you do instead is you create the master, or you create the stamp that's separated by this little membrane. Then when you apply when you inject a polymer into the master, the area of the stamp around the membrane will seal up by van der Waals forces and exclude the prepolymer from going in there. So that way you can get these little windows. So you can make the letter A, make these solenoids, make these interlocking rings. So here they're standing up, but then without the membrane they fall over. You can make these inductor type structures using this process. So these are, this is called particle replication and non-wetting templates. So one problem that you get with nanofabrication by stamping is that when you take suppose you have some polymer film on the floor and you step in it with your shoe, do you get discrete particles that correspond to the treads on your shoes? No, you just get an imprint, right? What if you don't want the thin layer in between the indentations on your shoes? That's called the scum layer or the flash layer. So it's like if you've got rubber galoshes. Bear with me. You've got rubber galoshes. There's a seam around the rubber galoshes. That's called the flash layer. So when you mold the plastic from 2 pieces, there's that flash layer that sticks out everywhere. You also get that in microfabrication by stamping. But if you have sufficiently low surface energy stamp, like perfluoropolyether, so this is like a Teflon-like material, you can take this and smash it into this prepolymer to get discrete particles. Now these discrete particles are can actually undergo endocytosis into cells based on what shape they are. So cells can figure out what shape they are, and they can engulf them for drug delivery and stuff like that. So we don't have a lot of time. I just want to make sure I cover everything that's cool. You can transfer patterns over and over using the same stamp, and you can stack them up. So these are these gold crate-like structures that were derived from films deposited directly on a PDMS stamp. Talked about phase shifting edge lithography, where you get nulls because of destructive interference at the edges of these relief features in the PDMS stamp that will now produce very tiny structures in this resist film. You can make 3D structures. So these are like photonic crystals. So if you take a photopolymer and you emboss the top of it with this topographically patterned stamp, then do a blanket exposure, you'll get a 3-dimensional diffraction pattern throughout the bulk of the resist film, which can be calculated and make these bicontiguous type structures. This is the cross section of what they look like, and this is actually an 3-dimensional interference pattern. So we've been talking about using 2D films to make 2D patterns. You can also make 3D patterns using optical interference. This is kind of a cool method by Michelle Kine at UC Irvine. So this is towards zero-cost manufacturing. So suppose you don't want to use photolithography or a clean room. All you want to use is a shrinky dink and an inkjet printer. Shrinky dink is biaxially oriented polystyrene that when you put it in the oven, it shrinks. So it's a child's toy, basically. But if you put ink on it by inkjet printing and you shrink it down by like a factor of 10, you can turn a couple micron pattern into a couple 100 nanometer pattern. And then you can make microfluidics for lab on a chip type devices for very low cost. You can use DNA polymers as self-assembly to make sub 50 nanometer features. This is an example of block copolymer lithography. I put it on here because we talked a lot about block copolymer. So this is the hexagonal microphase, where these are like perfectly registered PS PMMA, or sorry, PS polyethylene oxide block copolymer. And you can see all the dots here, and they're perfectly registered across several microns. This is graphoepitaxy. You can get the block copolymer films to form within edges. You can get them to bend around angles. You can get them to form these brain-like structures, brains. And in conclusion, lithography is great, and I'll see you all on Wednesday.